to lecture 9. Today we'll be talking about springs and Hooke's law. So first let's go ahead and define what Hooke's law is. So let's say I have a spring, for example, the spring of a pen, and I put one end of the spring against a flat surface, and I push down or I pull up on the other end of the spring, such that that end of the spring moves. So what happens is that there's a restoring force, right? If I push down on the spring, the restoring force pushes back up. And if I pull up on the spring, the restoring force pulls back down. So the way we mathematically represent this restoring force is with Hooke's law. So we say that the force is equal to negative k times x, where f and x are both vectors. So x represents the displacement. So if I pull my spring out, then x might be positive, and so the sign of f is negative to represent that we're pulling back in, or in general that the force is in the opposite direction, right? And same thing for the other way around. If I'm pushing in, the negative sign multiplies the pushing in direction vector for x and turns it into a force that pushes out. So a good way to think about the signs is if we drop the vectors and we just think about a one-dimensional spring. So let's say our spring is 10 meters long at equilibrium. When I say at equilibrium, I mean that if the spring is just laying there with no forces acting on it, it's not stretched, it's not contracted. So if I stretch it out 5 meters, then x is 5. And negative x is negative 5. So using the sign convention we've established for one dimension, positive is going to the right and negative is going to the left. So let's say I pull the spring out 5 meters to the right. Because the sign of that x quantity is positive, the sign of the force will be negative, and that's going to the left. And vice versa, if I push in, then it means that x is negative, and that's to the left. And so the force is to the right because it's positive. And you'll notice the k term here, f is equal to negative kx. K is a spring-dependent constant. It's measured in newtons per meter. You'll notice that that makes our units work out very nicely. We have newtons is equal to newtons per meter times meter, and it depends on the individual spring. So here's a quick example. We have a guy who is standing on a mattress that contains 100 springs, a spring constant 60 newtons per meter. And so assuming that each spring contracts 10 centimeters and that g is 10 meters per second squared, we want to find our man's mass in kilograms. So the key here is to understand that the forces acting on the man are gravity, which is pulling him down, and the spring force, which is pushing him up. The springs are contracted, so the springs push up, and that is the force that counteracts gravity and stops the man from falling. So here I've worked it out. I've set mg on the left side, that's the magnitude of the force of gravity, equal to n times k times x. So k is the spring constant, that's 60. X is the compression of each spring, that is 10 centimeters or 0.1 meters. We want to be consistent with our units here. And n is the number of springs, because each spring is providing a force of kx. So one spring is kx, two springs is 2kx, three springs is 3kx, etc. That's nkx is the total force provided by the number of springs. So we have 10 times mass, not 10 meters, but 10 times the mass of our man, is equal to 100 springs times a spring constant of 60 times a compression of 0.1 meters, which is equal to 60. That should say 600. I think it's being cut off. But dividing that 600 by 10, this is 100 times 60 is 6,000 times 0.1 is 600. So dividing that 600 by 10, we get mass 60 kilograms or 132 pounds. So springs are part of a wider class of systems called simple harmonic oscillators. And what's special about simple harmonic oscillators is that their motion can be described in terms of a second order differential equation of a coordinate of our choosing. And of course that's calculus, and we don't necessarily need to get into that, but what you need to know here is that for springs, because of the form of Hooke's law, which sets acceleration proportional to force, we're able to use calculus to derive these formulas for the position, velocity, and acceleration of whatever object is on the end of the spring, whether that be my finger or an independent mass that's bobbing from the end. So kind of the hallmark of simple harmonic oscillation or simple harmonic motion is the sinusoidal motion. I'm sure you know what a sine wave looks like, what a cosine wave looks like. You should have seen that in trigonometry class. And basically, that's what the coordinate of our mass on the end of the spring, or my finger on the end of the spring, looks like. If I were to plot its position on the x-axis and if I were to plot time on the y-axis, time on the x-axis and position on the y-axis, then I would get a sine wave. And that is what simple harmonic motion looks like. So by solving Hooke's law using calculus, we get that x, the position of a mass on the end of the spring, or of the end of the spring in general, is equal to a times the sine of omega t plus phi. So here, a is the amplitude of the motion. That's like the furthest out the mass gets, or the furthest in the mass gets. So when the mass is at the amplitude, it's a distance a away from the equilibrium length of the spring. It has a velocity of 0, and it's accelerating inward because it's going out, it's stopping, and then it's coming back in. And omega is what we call the angular frequency of the spring, and that basically defines how often a cycle occurs. It tells us how compressed or expanded our sine wave is. It tells us, like, a higher angular frequency means that more cycles of motion are occurring per second. It means that our mass is bobbing up and down faster. And a lower angular frequency means the opposite, it's going slower. And phi is what we call the initial phase, or just the phase. And what it means is that basically, let's say phi was 0. Then we'd have that x of 0 is always equal to 0. But what x of 0 is really depends as much on what we define t to be as it does the parameters of motion. For example, I can say that when my mass is at the amplitude, when it's at the absolute maximum of its motion, that's t equals 0 instead of when it's at the equilibrium length. And so really it's a matter of definition, and what phi lets us do is it lets us qualify that initial condition mathematically. So if phi is equal to 90, then we get a cosine wave. And that means that, well, when I say 90, I mean 90 degrees. That would be pi over 2 radians. But what it would mean for phi to be pi over 2 radians is that our spring is starting, our spring's position, the position of the mass on the end of the spring to be exact, is starting out of the amplitude instead of at equilibrium length. And so that's what phi lets us quantify. And next we have velocity, which is equal to a times omega times the cosine of omega t plus phi. And acceleration is equal to negative a times omega squared times sine of omega t plus phi, which is equal to negative omega squared times x. Notice that. You may notice if you've taken calculus that we're basically taking successive derivatives to find velocity and acceleration. That's because velocity is the time derivative of position and acceleration is the time derivative of velocity. So note, going back to Hooke's law, that f is equal to negative kx, and Newton's second law states that that is equal to ma, and our formula for acceleration we just found tells us that ma is equal to m times negative omega squared x, or negative m omega squared x. So setting negative kx and negative m omega squared x equal to each other, we get that omega, our angular frequency, is equal to the square root of the spring constant k over the mass m of what is at the end of the spring. And that the period t, which is how long it takes for a single cycle of motion. A single cycle of motion would be like, let's say we have the mass bobbing at the end of the spring, right? So the mass goes down to the amplitude where the spring is stretched out as much as it can be, and then it goes back up to the middle point, then it goes up to the amplitude where the spring is as compressed as can be, and then it comes back down to the equilibrium length again. And we're assuming that we started at equilibrium length. So that would be a single cycle of motion, and the period tells us how long in seconds it takes for that to happen. And then we have f, the frequency, which is just another way of quantifying how fast cycles are occurring. We can use angular frequency and frequency interchangeable. The advantage of frequency is that it converts more naturally to period, but it doesn't convert as naturally to spring constant as angular frequency does. But you can use either of them. So here's a quick slide that is defining these quantities again. So we measure initial phase in radians because sine takes in an angle, and we measure angle in radians. And angular frequency is in radians per second. Period is in seconds because it's measuring time, and frequency is in inverse seconds. So not radians per second, but inverse seconds. And you notice that if we go back, we had that frequency is equal to omega over 2 pi. Omega is measured in radians per second, and 2 pi is measured in radians. So dividing out the units there, we get inverse seconds. And another name for that unit is the hertz, or Hz, which I'm sure you're familiar with if you've ever listened to the radio or worked with computer processors. When you listen to the radio, the hertz over there is describing the frequency of the radio waves that carry the radio signal to you. And when you're working with the CPU, the frequency is describing the number of clock cycles that the CPU is going through, or how fast the CPU goes through a clock cycle. So let's do an example. At time equals 0, a mass on the end of a spring with spring constant k is moving with velocity q, and it's displaced from equilibrium by a distance of p. Given the amplitude of the mass's motion a, find its period t. So let's go into the solution. So using the formulas for position and velocity of simple harmonic motion, we get that a sine of phi is equal to p, and a times omega times the cosine of phi is equal to q. Notice that the omega t terms have disappeared because t is equal to 0. We're only working with initial time and position, and velocity here. So rearranging these equations, we get that sine of phi over p is equal to omega of cosine over q is equal to 1 over amplitude. And that, if we rearrange again, we get that phi is equal to arc sine, or inverse sine, of p over a, which is equal to the arc cosine of q over omega times a. So setting arc sine of p over a and arc cosine of q over omega a equal to each other, we get that q over omega a is equal to the cosine of the arc sine of p over a, which is equal to the square root of 1 minus p squared over a squared. That is a useful trigonometric formula. And we wanted to find the period of motion, and remember that period is equal to 2 pi over angular frequency. So 2 pi over angular frequency is equal to 2 pi times a over q times q over omega times a. Times q over omega a, this quantity that we found earlier in the fourth line, which is equal to 2 pi times a over q times the square root of 1 minus p squared over a squared. So this is a very complicated formula, and you may not be convinced that it's correct. I certainly wasn't when I found it. But a good way to check again is through dimensional analysis. And so let's work through. Over here, let's enable my pointer. Over here we have, let's start with the square root term here. We have 1 minus p squared over a squared. P has dimensions of meters. A also has dimensions of meters, so this is dimensionless. and so is this 1. That means that this entire quantity is dimensionless, as it should be, since we have a cosine, and cosine takes in an angle and returns something dimensionless. Arcsine takes in something dimensionless and returns an angle, and angles are measured in radians, for what it's worth. So P over A, as we said earlier, has no units because both P and A have the same units, and those units cancel each other out. So dimensionless, angle, dimensionless. So this has the same units as this. And this over here, we have Q, which is measured in meters per second, over radians times meters per second. So that gives us that gives us inverse radians, I think, which is fine. It's not something to worry about that much. Radians can go in and out. But the real test is down here, where we have period and this massive formula over here. So period is measured in seconds, 2 pi is measured in radians, and omega is measured in radians per second, so this comes out to seconds. 2 pi times amplitude over q is radians times meters over meters per second, so that's radians times seconds times dimensionless, so we get radian seconds, which is, as I said earlier, it's acceptable. That's fine. So yeah, basically, using dimensional analysis, we've shown that our formula is basically correct. Or at least it stands the rigor of dimensional analysis. And so yeah, that's a good way to use simple harmonic motion. And simple harmonic motion will show up over and over again. It is very easy to model any system as simple harmonic motion because once you realize that a system is behaving sinusoidally and you see a force law that resembles Hooke's law in that it sets, acceleration equal to proportional to position, you can immediately slap down these sinusoidal equations and get to working on how the system behaves. So yeah, that is all for today's lecture. Before we end, I want to clarify Hooke's law. Hooke's law describes a mass on the end of a spring. Using Newton's second law, we know that force is equal to mass times acceleration, and it's easy to lose sight of what we are describing. So Hooke's law describes the mass that a spring exerts on a mass at its end. So the mass is at some position, x, at the end of the spring, and its acceleration is a. And so we set negative kx equal to ma, and we solve. But it's important to remember that we aren't describing the motion of the spring. We're describing the motion of that mass at the end of the spring. The spring, usually, in fact, we assume it to be massless and stationary. If a massless spring has a force on it, then it's going to accelerate infinitely. Because F is equal to 0 times acceleration, and F is non-zero. That gives us an undefined acceleration situation. And so, usually our springs will be massless and immobile, and we're always going to look at that mass on the end. That's what we use Hooke's law for, and that's what simple harmonic oscillation describes. It describes the motion of that mass. So yeah, thank you for watching this lecture today. If you have any questions, feel free to ask. And yeah, next time we will be covering more simple harmonic oscillation, including another kind of simple harmonic oscillator. Thank you.